brought from Professor of Art. Something a little different for tonight, okay? Now, in 2 weeks, we have another Science Cafe, and that's going to be Claudia Gonzalez Vallejo from Psychology. She'll be presenting her research on how judgment and decision-making in regard to nutrition may change food labeling policies. Okay? And then on the 26th, we have a cafe conversation in journalism and communication, and they'll be presenting on infographics and how journalists use them in reporting. So those are a few of the things in store for us in the coming weeks. But right now, let's see what art and civil engineering have to do with each other. Thank you.
All right, I'm not really used to a mic, so this might take some navigating for me to get that right. Does that sound okay over there?
A little closer.
Closer? How's that? Is that better? How about that? Oh, I can hear that back.
You can hear it back, you're good.
Yeah, okay. So that's what it's supposed to sound like. All right, so I'm Kyra. I'm a professor of environmental engineering. I got my degree in environmental engineering focusing on cleaning up pollution. And when I got my degree, my specialty was really cleaning up explosives at military bases. And I took a job here, and I got out here, and I was like, well, now what am I going to do? There's no bases around here. So I looked around for pollution, and unfortunately, you can find pollution pretty much anywhere if you look for it in this country. So I'm going to talk about one of the biggest pollution problems in the region here, and what we're trying to do with it. So I'm going to start a long time ago, 360 million years ago. This is before dinosaurs. This is in what's called the Carboniferous period. This is the age of Pangaea, where all of the land mass was a single continent. The climate and temperature was very strange back then. It was perpetually hot and tropical. And where we're standing right now, there were massive swamps with giant trees and all kinds of incredible foliage that lasted for about 60 million years. So 60 million years, if you can think about that length of time, all that stuff, all those plants were taking carbon dioxide out of the atmosphere and turning it into wood and leaves and roots, which accumulated and accumulated and accumulated for 60 million years. So what became of all that stuff? Do you think?
It became cold and all.
Cold. Exactly. That's why we call it the Carboniferous period. This was a period in time that was very productive on the planet. These plants were taking solar energy and turning it into stuff, and all that stuff got fossilized through pressure and heat and stuff that I don't understand, and produced tons and tons of coal, which is used to be underneath us right now. So this, as you know, this is a massive, very useful energy source. 60 million years of solar energy, all stored in these rocks that are underground, and all we have to do is dig them up and we can harness that energy. So for, I don't know, probably over 100 years now, we've been digging up this coal and burning it. And this is one of the mine maps for one of the mines nearby. And you can see the old mining technique. They use room and pillar techniques here. And what you can see is they basically tunnel these labyrinths and catacombs through the ground to pull out as much coal as they can without having the ceiling collapse on it. So that's why they didn't like sweep out all the coal, because then it would just collapse and fall on it. They made these little rooms so that the columns they leave behind would pull up the roof. So these deposits from 360 million years ago all of a sudden are exposed to air and water. And all kinds of crazy things happen when you do that. This is another picture showing sort of the extent of mining in our region here. OU is down there. And you can see the shaded area there has all been mined out by underground mines. So as you drive around here, when you're driving through like Wayne National Forest or on Route 33, and you see all these sort of forested hillsides, just imagine that there are holes and catacombs underneath most of them as you're driving through. Okay, so now I'm going to get into a little chemistry. As these deposits, which have been buried and protected from this very oxidizing environment that we live in, these things that have been underground for 360 million years are suddenly all exposed to air and water. And not just coal is there, right? There's lots of different things in plant matter. And one of the things that also accumulated in this deposit was pyrite, which you can see here. So when that reacts with oxygen and water, it goes through a whole series of chemical reactions, producing, among other things, sulfuric acid and iron oxide hydroxide. Okay, so this is what comes out of the mine. This is acid mine drainage is what we call it. This is heavily polluted water. Okay, doesn't really look so bad, right? Looks like something you might come out of the tap. In fact, I wanted to make sure I didn't mix up what glasses I was drinking out of here. But this is what it looks like coming out of the mine. This is high in sulfuric acid and high in a reduced form of iron called ferrous iron, which is in that first reaction there. And this is what it looks like when it pours out of the mine. And we have lots of mine seeps throughout the region where this is just pouring out 24 hours a day at very large flow rates. As it flows down the stream, it splashes around, gets exposed to oxygen, and as the oxygen reacts with the water, these reactions take place. And what you can see, I hope this works, is that iron changes form. So iron is a very interesting metal in that it has multiple oxidation states. It also has multiple minerals that it can form. It's a very flexible element, I guess you could say. So this is what our streams end up looking like when they're polluted with acid mine drainage. Yeah?
That's pure water in that.
This? No, this is an oxidant. What I just poured in there is hydrogen peroxide.
Oh, hydrogen peroxide.
And so in the streams, it's oxygen that works as an oxidant. But this is better for demonstration.
I understand it.
Okay, so these are some pictures from the neighborhood, basically. This is the True Town Seep. This is maybe 20 miles from where we're standing. This is a 30 square mile mine complex that in 1982 or something erupted in someone's backyard. 1 million gallons a day pours out of that every day for the last, I don't know, what's that, 24 years, 34 years, and it's still going today, and nobody is cleaning it up. This is another stream in a different region, but this picture up here shows you every one of those diamonds is an acid mine drainage seep in Ohio. So you can see where all the mining was done, and that's where all the pollution is. Okay, so, yeah?
So, did the water just, is it from rain and years and years and years of rain? Where did the water, and then it went into the mine and now somehow it's working its way out? Is that what's happening?
Yeah, well,
Groundwater coming up and getting into the mine?
Repeat the question.
oh, thank you. So the question is, where does the water come from that generates all this acid mine drainage? And when they're working the mine, many of these mines are below the groundwater table. And to work the mine and capture the coal, they have to put on pumps to lower the groundwater table and keep the water out of the mines. But when they're done, before there were regulations on it, they just turned off the pumps and walked away. The mines flooded, and then the water started coming out. Yeah, great question. So this, if you're a fish, this is a big problem, okay? It makes everything you do in life difficult to live, and we find streams that are heavily impacted by acid mine drainage have really poor fish populations. Some of them are devoid of native fish that should be there. So these things are devastating to the local ecology, but in some ways they are natural. Okay, so it's just iron. It's not in itself toxic. And you can find these deposits throughout the world. And for a long time, well, since the beginning, we've been using these materials. So this is a cave painting from France. And all of these cave paintings use just a few different colors: black, red, orange, yellow. The red, orange, and yellow all comes from these iron oxide deposits. So that got us thinking about, well, we've got pollution. It's too expensive to treat. But you can go out and buy iron oxide pigment, and it's sold for a pretty good price. So how about we take this pollution and sell it? I did a little looking around, and the first couple articles I looked at, other people have looked at this and they said, it doesn't work, the chemistry's not right. But I did a little more searching, and I found this color, I don't know how to say it, Falun red? There's a mine in Switzerland that for the past 400 years has been collecting their acid mine drainage and turning it into paint. And this color is like the national color of Switzerland, if there is, if you think of such a thing. And it's got, you can see it's a gorgeous color, it's this nice bright red. Their mines are a little different. This is a copper mine, it's got chemistry different, but it inspired me. The other thing I found out is that the pigments that we use in the United States today, it's an enormous market, 50,000 metric tons per year. That's a lot of pigment. It's a $50 million market. Oh, that's just U.S. production. We import 178,000 metric tons every year, most of it from China. And a lot of it is produced, the majority of it is produced synthetically through this sort of water treatment process. So that also gave me inspiration as to what we can do. So then for about 10 years I was collecting acid mine drainage, putting it in jars, trying for oxidants and different chemical techniques. And we were using tubs from Walmart, and bubbling and mixing and measuring pH and doing all these tests. And I produced a lot of like really bad paint. A lot of like brown and like baby poop color, just stuff that, and I would send them, and I send a couple to paint companies, and they were like, no good. So I had to get a little more sophisticated with the chemistry, and the iron chemistry is very interesting. As an element, it can form a variety of different minerals. I'm only showing 3 here, but there's probably 8 or 10 different minerals, maybe even more, that iron can form just using oxygen and hydrogen. And so ferrous iron is what comes out of the mine. That's clear. You then oxidize it to ferric, and then very quickly, depending on conditions, it will precipitate as a mineral. And the problem I was having is I was producing a mixture of all of these things, and that has no value in the marketplace. But if you can direct this precipitation process towards one mineral or another, like hematite or goethite, those have a very, or magnetite. So magnetite's black, hematite's red, goethite is yellow. Those have a lot of value in the marketplace. So I was playing around with this, and color isn't very good here. But we started to come up with some conditions in the lab that we thought would work. We started to understand the chemistry a little better, how to control that precipitation process so we can produce more pure paint. One way to test for mineral content is powdered X-ray diffraction. And that's what this figure shows. So this is like one of my brown, sort of nasty things. And the blue, you can see the blue lines are just all over the place. The red line is our target mineral. And when I produce it under a different condition, I can get much closer to my target. You can see the blue lines map to the red spikes very well. So I'm producing fairly pure mineral with that. And under different conditions, I can increase the iron content in my final product. And we got to the point in the lab where now we could produce high quality pigment, at least what I think is high quality pigment. It won't really be high quality pigment until I can get someone to buy it. But it looks good at least. So where we are in the process right now is we understand the basic science. We understand the factors involved to make good pigment. And right now we're seeking money to build a plant to do this full scale. Well, to do this pilot scale. So the idea is you go to one of these sites, like that mine that's pouring out of someone's backyard, and you build a water treatment plant right there. And as the water comes out of the mine, it goes into your plant. And through a series of processes of aeration and settling, and then filtration and neutralization, you can take the iron out of the water, collect it in a sludge, process the sludge so you end up with a nice powder which you can then sell.